first, here are the homeworks that have been graded. If for some reason you didn't turn in the homework that you had graded on Friday, put it right here. Second, what we're going to do today is talk about Numpy arrays and the Numpy library. So, by the way, get your graded homework out of this folder as it goes around. So we'll talk about Numpy arrays and the Numpy library today. And then on Wednesday, which will be the last day of the sort of scientific computing aspect of the course, I'm going to talk about symbolic and numerical calculus type stuff. So this will be about how to do trivial and sophisticated symbolic integration in Sage, computing limits, simplifying expressions, and so on, and also computing numerical intervals and numerical integration. Sage has really extensive capabilities for numerical integration and for doing symbolic integration and so on. So, I just rebooted my computer in the hopes of getting internet access. Okay. All right, so Numpy is a library that's included in Sage. It's has a long and colorful history. So it's really a derivative of two other libraries, one called NumArray and another one called Numeric. And it's really I guess it's kind of the brainchild of Travis Oliphant, who's one of the main people at Nthot. So it's a little action delete all out. All right, so there's a book. There's a book on NumPy, which it's an electronic book, and I have. If you download the Sage worksheet, then click right here. You'll get a copy of that book, so you can look at it. It will be made freely available pretty soon. It's actually available under a really weird license, which basically says it's going to cost a lot of money until 2010. But the main reason for that was that the guy who wrote it, Travis Oliphant, was a starving professor, and so he needed money to support what he was doing. And then he sort of, his academic life didn't really work out, and his industrial life, that is to say working in industry, suddenly started looking extremely good. And so he quit working at Brigham Young University and took a very good job at Nthot, which is the company that sponsors SciPy and NumPy. They're kind of they're a huge well, not huge, they're actually tiny open source scientific computing consulting company with somewhere around roughly 20 employees. So, so here's this book. And I think now that he has a much better job and so on, he's going to just make this book freely available very soon. So that's kind of a little bit of the background. NumArray and Numeric, these are both Python libraries for working with matrices, and they go way back. I think Numeric goes back maybe, I don't know, 8 years or so. Basically, a lot of people like using Python for doing numerical computation, and it's not at all a new thing. So NASA, for example, and various people doing a lot of analysis of large data sets have needed to be able to compute with matrices or arrays that have floating point entries. And they've done so, and I think Numeric was the first big library for doing that sort of thing. It was rewritten, I think, quite a lot to make NumArray, and there were interesting optimization choices that were made in rewriting it. So for example, with NumArray, you find that the people that rewrote it, they cared a lot about massive matrices, huge, huge matrices. So they rewrote it in such a way that for very, very large matrices, it was fast. But for smaller matrices, it was substantially slower than numeric. So the result of this was that people continued using numeric and NumArray at sort of the same time. And it basically just broke the community in half, which was a big mess. So Travis Oliphant, this one guy, just sat down and worked very, very hard for a couple of years to try to unify these two and make something that was significantly better than either of them. And it would really bring the community of numerical Python people together. And he did it, and the result's NumPy. The first time I ever saw Travis Oliphant was at Caltech at the 2006 SciPy meeting, and it was when he was accepting a big award from this scientific Python community, where they were just saying, thank you for unifying us and providing this NumPy library, which is really making our lives much, much easier. So that's kind of where NumPy comes from. And given that Travis now works full-time at Enthought on Python, and that everybody's using NumPy, it's clearly an excellent choice for what it is. So the question is, what the heck is it? So the first thing is it's a Python class for working with arrays, with n-dimensional arrays. In other words, vectors, arrays like tables, like a spreadsheet sort of thing of data, or an image or something, or three-dimensional arrays. So a three-dimensional array, you can imagine, an example of this might be the red, blue, and green color channels for an RGB image. There you have three separate arrays of numbers between, say, 0 and 1, or 0 and 255, whatever. And the 0th entry in the array you can think of the three separate arrays as one single three-dimensional array. And that's kind of the idea with NumPy. And it's really something that's very unique and very popular in scientific computing, but supported extremely well in NumPy. So instead of thinking of an RGB image or whatever as being three separate arrays giving the red, green, and blue values, you can think of it as one single three-dimensional array. That is, it may be a 800 by 600 by 3 ND array. Or you could imagine having a bunch of volumetric data. So at each point in the room, you've measured the temperature. And now you can take this data and stick it in a three-dimensional array. Or maybe at each point in the room, you've measured something more complicated than just the temperature. And at each point, maybe there's a three-dimensional piece of data. So then you have an even higher dimensional array. Okay. So that's the idea of these ND arrays. And so NumPy isn't, I really have to compare it to Sage matrices. And it's really drastically different than Sage matrices in almost every possible way you can imagine. NumPy ND arrays are designed for scientific applications. Every step of their development, all the motivation for them, is just 100% scientific computing. People have large data sets that they get from running simulations, whatever, and doing optimization problems, anything. They want to manipulate that data to solve the sorts of problems you solve in scientific computing. And as a result, a lot of the design decisions and functionality that ND arrays support, that NumPy arrays support, are a lot different than the matrices in Sage. The matrices in Sage, the matrix type, so just to remember, in Sage you make a matrix by just saying, matrix, then you give a ring, say that the entries are over, and then you give maybe the entries of the matrix. These are very kind of mathematical objects. They are supposed to be a lot like the matrices that you encounter in a linear algebra course. So they basically represent linear transformations between vector spaces. That's really what matrices are in the context of linear algebra. So for example, one characteristic of matrices in Sage is that very clear at every point you're always specifying what the data type is of each of the entries. There are lots of specialized algorithms and functionality depending on the data type. But also, the entries all have to have exactly the same data type. There's no support for doing anything else. they are two-dimensional because in mathematics, if you start talking about higher dimensional arrays, you start thinking about differential geometry, tensors, etc. I mean, you can always, you wouldn't think, I mean, to a mathematician, you wouldn't think of so much a higher dimensional array as an array whose entries are elements of some ring, where that ring is of higher dimension. So for example, with the color example, a more mathematical way to think about that would be it's a two-dimensional array, each of whose entries are a point in some space, that sort of thing. So there's a very different perspective between NumPy and Sage. Sage matrices, just to summarize, they're really, for the most part, modeled on matrices in magma. They have a clearly specified base ring. They have optimized algorithms for working over that ring, and they're 2x2 matrices. They're supposed to be like matrices in a linear algebra course. You care a lot about data types where each entry can have arbitrary precision. The underlying storage format, for example, for a lot of the Sage matrices, each entry can have a much different size than each other entry. So for example, with an integer matrix, one entry could take 7 megabytes to store, the other entries might take a few bytes to store, and another entry takes several megabytes. That's a much, much different kind of situation than with NumPy arrays, where all of the optimized NumPy arrays have the property that every entry of the matrix takes exactly the same amount of space to store. Okay, so also if you make a matrix in Sage, as you have already done many times, you'll notice that the functions all have kind of a, I don't know, they're very mathematical. So you have things like asking for the rank, the characteristic polynomial. There are a lot of functions that hardly make any sense in the numerical context, but make a lot of sense algebraically, etc. In NumPy, the NumPy arrays have tons and tons of functions that don't really make any sense from the point of view of linear algebra, but are incredibly important in numerical computation. So the typical sort of flavor, if you opened a random page in the NumPy book, of the sort of functionality you'll find for a NumPy matrix is, given a NumPy matrix, there's a function that will truncate it. That is, it will take all the entries, and if they're bigger than a certain value, it replaces it by that value. If they're smaller than a certain value, they replace it by that value. Or they'll take the matrix and compute the mean of the entries in the matrix, or the variance of the entries in the matrix, do a whole bunch of standard statistical operations, or compute the fast Fourier transform of the entries in the matrix. This is the sort of thing you'll find tons and tons of functions for NumPy arrays. So it's just these two different worlds, and in Sage you have both of them. So you have to know which to use. So if you try really hard to use Sage matrices to do too much in the way of numerical computation, you could easily get really frustrated because the sorts of functionality you want to use possibly won't be there. And you shouldn't just get really frustrated. You should crack open the NumPy book or make some NumPy matrices and start looking at them and see that, in fact, maybe for what you're doing, it would be very easy in NumPy. Okay, so now I'm going to show you how to do lots of actual things in NumPy to give you a feeling for how NumPy really works. Okay, and lots of explicit examples. There's one thing, for example, that's really useful in NumPy. It's kind of amusing. There's one kind of extra NumPy array type, which, unlike all the other NumPy array types, where each entry has to have exactly the same size, allows completely arbitrary Python objects as entries in the NumPy array. And if you just do import NumPy, and then you do numpy.array, you can make an array that has entries that are absolutely any Python objects you want. You can put anything there. You could put an image there, you could put symbolic expressions, a random matrix, a floating point number, and 2/3. It's totally different than what you have with the Sage matrix, where all the entries have to have the same type. So here you get an array, and it could be it doesn't have to be a two-dimensional array. This is an array with two different dimensions, rows and columns. You can make a 5-dimensional array, that is where each entry of the array is entries are indexed by 5 tuples of integers, where the elements of the array are arbitrary Python objects. And then you have a huge amount of functionality for them. And you can do arithmetic as well. Arithmetic makes sense in the objects. Notice here the printing looks really, really hard, or looks really bad. Part of that is because it's using ASCII art to display this symbolic expression. So so it looks terrible. I wish it didn't do that. Fortunately, I just wrote a little function down here called show numpy. It takes as input a numpy. This takes as input a numpy array, possibly an n-dimensional numpy array, and it will display, nicely typeset on your screen, that numpy array. So this is the code that does it. And it illustrates various things that I'm going to show you in a minute involving how to work with numpy arrays. For starters, I'll just run it. Here was the array I made just a moment ago. Notice it has a random matrix, a symbolic expression, a floating point number, and a rational number, all in the same array. So if you find yourself doing some sort of problem, and it would be really good to have such a weird mix of types, and you just want to keep track of them, and an array is the right kind of thing to use, then use numpy arrays. And there's a huge amount of data analysis problems that involve arrays. That's why spreadsheets are so popular. I mean, an array is just kind of the sage version of a spreadsheet. By the way, if you want to multiply, so this is a big gotcha to watch out for. If you do show np z times z, it just multiplies the entries component-wise. So this is a perfect example of the difference between having a very kind of data manipulation point of view on arrays and having a very mathematical point of view on arrays. With numpy arrays, star, quote, matrix multiplication is just component-wise multiplication, as you can see. It just multiplied each thing component-wise. Whereas, of course, in Sage, where matrices are supposed to be mathematical objects like you have in a linear algebra class, matrix multiplication is standard multiplication. If you want to multiply in the sense of mathematical matrix multiplication, you use numpy dot, the dot function. That will multiply the two matrices.
The exact opposite of how it does it in MATLAB. It's MATLAB, the dot does component-wise multiplication.
Is that true? If you're a MATLAB user, I'm not sure if I agree, but there's a nice page that compares NumPy and MATLAB, and it has examples of how to do everything, called NumPy for MATLAB users, like you. And it has this really nice table of equivalent functionality. So let me zoom in because it's hard to see. So for example, this has the command you would type in MATLAB, and then the corresponding command in NumPy. Actually, I'm not really expressing skepticism, I just don't know, so that's why I'm putting this up.
Dot star is component-wise.
Dot star.
Dot
Okay.
star.
So let's see what if it has an equivalent. So it has all kinds of transpose. Here we are. So a normal star in MATLAB, as exactly as you said, is matrix multiplication. In NumPy, it's dot AB, whereas it's dot star in MATLAB, and it's component-wise there. And then dividing component-wise is just slash. So there's a kind of an index here, but I don't know. I find this really annoying, to be honest, that matrix multiplication is component-wise by default. But I guess if you don't have, so there's no possible way NumPy could do dot star because that isn't valid Python notation. So they figured, I guess, that star is much, that wanting to multiply component-wise is apparently much more common for numerical people than actually wanting to do matrix multiplication. Any numerical people have any comments? I don't know. I mean,
I'm skeptical of that argument.
in algebraic computation, everything is matrix multiplication. So that's the most common thing you ever do. But I mean, I'm guessing at psychology, and that's all. So take it or leave it. But by the way, while we're here, there's this big table which, like you'll know, you'll probably, if you've ever used MATLAB, you'll know that it has some really nice syntax where you can slice matrices and get submatrices. And NumPy has very similar syntax. So for example, A1:5 in MATLAB, well, because it's zero-based, becomes A0:5. So it's actually really similar. This translates into that, etc. Basically, it's just shifted a little because it's zero-based rather than one-based indexing for consistency with Python. But otherwise, you do have slicing So it's pretty nice. So making diagonal matrices, making random matrices, etc. There's a lot of similarities between NumPy and MATLAB. Okay, so this. There's an example of a 1D array. Now the next example is a 3-dimensional array, which really isn't that scary. So all I've done is made a list of 2x2 matrices, but then I consider that as a 3-dimensional array in NumPy. So a 3-dimensional NumPy array. And so you index into it by giving the 3 entries. So for example, if you go if you do m, I don't know, 1, 1, 1, what do you think you're going to get? Two. I agree with that. Let's see. You get 2. By the way, the type of the thing you get back when you do this indexing, I made a matrix whose data type is int. It's actually not a Python int. It's some sort of light wrapper around a C int, a 32-bit int. And you look at its type, it's just numpy.int32. If you want to get back a normal Python integer, you have to do .item on that, and it'll give you back a normal Python integer. So so the thing is, with NumPy arrays, you can give this option dtype equals, and that will explicitly specify that all the entries in the matrix should have that one homogeneous type. And that's what most people do when they're working with NumPy matrices. So typical examples are like int 32 and float, for example. So we could take the same matrix and say dtype equals float, then all the entries would be stored as C doubles, as you can see. Or actually, yeah, 64-bit C doubles. So you have that dtype object. And literally in memory, it creates an array of, a C array of doubles. So there's, I think there are about 21 different NumPy data types. So ints, there are different size ints and different size floats and so on. And the key thing about these is every single one except pure Python object of these data types is some fixed width, basically C-level data structure. So it's some very, very simple thing. So here's an example of there's an extreme amount of flexibility working with NumPy arrays that, from a kind of mathematician point of view, can really make you very nervous. And I'll show you quite a bit of that. So for example, if you just, at any point you can take a NumPy array and just set its dtype to whatever you want. So you can just set its dtype to be float. And suddenly the entire matrix, what it does is it just takes exactly the same memory and pretends like the things in that memory are floats. So it's not coercion, it's literally, let's just pretend like this raw memory consists of a bunch of 64-bit doubles instead of 32-bit ints. And you can see that the meaning of that is a little questionable because, for example, 2 becomes this very small number right here. Actually, there's less numbers too. So I guess actually -5 and 2 becomes that number. So this is the sort of thing that, if you're worried about rigorous mathematical computation, if somebody suggested functionality like this for Sage matrices, we'd be like, yeah, right, no way in hell we'd ever, let that go into Sage. But on the other hand, imagine you really know what you're doing. You're doing lots of numerical computation. You know what the memory means. This is a completely reasonable thing to want to be able to do. So just a different world. Sage supports both of them, and NumPy is much more on the scientific side. Let's change it back. There it is. It's back. It's an integer matrix again. It's actually a wider integer matrix, just like that. So it seems crazy, but I bet the devious programming people among you are already thinking of ways that you could take advantage of this. So don't knock it. But don't try to change Sage matrices to be like that, because they both have their place, I think. Oops. So as type, this is a better function. What this does is it takes the matrix. This is much more like changing the base ring of a matrix. So it takes all the entries and turns them into floats and makes a corresponding matrix. So it's allocating new memory and then filling it in a meaningful way. So as type is much more rigorous than just setting the D type in a sense, or at least it has more mathematical meaning. Here's another attribute that matrices have, flags. So this tells whether the matrix can be changed, how it's aligned on memory, whether the matrix owns its own data or it's just a pointer into another matrix. So another thing that ND arrays are extremely good at, and this can be a serious confusing point if you just jump in and start using them and expect them to not work this way, but if you take a big old Numpy ND array and then you slice it using kind of MATLAB-like syntax to get a submatrix, you literally get a submatrix of the original matrix. It's just a pointer into the memory of the original matrix and some information about stride and whether the matrix owns its own data or not. So in that case, its own data would be false. So if you want to take a big matrix, get a submatrix, do something algorithmic on that, etc., Numpy is really good because you don't waste any time making a copy of that submatrix. This is totally different than with Sage matrices. With Sage matrices, if you slice into a Sage matrix using the slice notation, you get a whole new matrix as the submatrix. And the semantics in MATLAB are similar. In MATLAB, if you slice into a matrix, you get a different matrix. What it'll do is it'll lazily try to make it the same matrix until you change something, and then it'll make the copy. So this is a massively different semantic way of thinking about matrices. The meaning is just different. Slicing gives you a submatrix, literally. Let me illustrate that in case it wasn't sufficiently clear. So I think I want to do that. Okay, so here is a slice of that three-dimensional matrix up here. Okay? Here it is. Maybe I'll do show for consistency. So there it is. Notice that what I've got are some of the entries. And now I'm going to change one of the entries of this, quote, new matrix A, which a normal Sage matrix, it would literally be a new matrix. And you'll see that it changes the original matrix. So I'll change the 0, 0, of A actually, I'll change the 0, how does this work? I guess the 0, 0, 0 entry to that big number, right there. Okay, now let's look at the original matrix M. Wow, so it changed the original matrix. So watch out for that, that's kind of a gotcha. But on the other hand, again, if you know that that's how things work, you can immediately start thinking of how you could use that to implement algorithms more efficiently, where having windows into other matrices is actually extremely useful. And you can always get a copy out, or copy a given matrix if you need it. So for example, if you really needed the, if you really needed A to be a copy, you could do dot copy. And then that gives you a truly different one. So by the way, here, oops. If I make this, then the flags are different. Oops. Flags. See, own data is equal to false. Now, a really crazy thing is you can change these flags. And so, for example, you can change the writable flag. So here's an example of that. Back to our matrix M has these flags. One of the, let's see, let me actually have an example. Where's that example? Well, I can do it from memory. So you have these different flags. And one thing you can do is say, change the writable flag to be false. And then that makes it so you now can't change the entries of this matrix, or you get an error. So this is like setting a matrix to be mutable, or immutable in Sage. So there's a command set immutable for Sage matrices that makes them so you can't change the entries. But here's the crazy thing about Numpy arrays. You can just set the flag to be true again, change the matrix, and then set it to be false, and nobody knows the difference. So look, I just set it to be true, and I can change the entry. So it's kind of pointless, but oops, I need to show no. So notice we could just do this. So it's not really that strong of a constraint that you set it to not be writable. And the way this sort of thing can come up in kind of mathematical algorithms is, let's say, for example, that you you have a group, and it's acting on some vector space. So you have a group representation, and you compute the matrix for the action of a certain element of the group on the vector space. And because it's very expensive to compute that matrix, you cache it. That is, you store it with the group and its representation. And you, of course, would want to set it so that it can't be changed, because you wouldn't want to return it to some other function that just changes one of the entries of the matrix. Because then if you use it somehow else, say to compute something about the character table of the group, then you're going to be in big trouble. So in a lot of algebraic algorithms, you compute matrices, which are invariants of some abstract algebraic structure, and you return those matrices, and if somebody else does something to them, you're in all kinds of trouble. But you don't want to have to return copies because it's very expensive. So what you do is you set it to not be writable, but with Numpy, if you're using Numpy arrays, then whoever wants can just turn off this writability immediately. So it's yet another thing to keep in mind. Okay, next, I'm just going to show you some of the other properties of Numpy ND arrays. So strides shows how many bytes you have to jump to get to the next array entry in a given direction. So it's just a useful thing to record. So for a 2x2 matrix, it would be like the number of columns times the number of bytes that each entry takes, that sort of thing. So this is really useful because since all array access for ND arrays goes through this stride stuff, you can have a matrix that's a submatrix of another matrix. And doing things like changing the data type, you just have to change the strides as well, etc. So it's, I mean, again, one of the things about these ND arrays is that they really, really are trying to model having this homogeneous data structure in memory that you, as the user of this, actually know something about. It's not supposed to be too abstract. So it doesn't try to hide the details of underlying storage. Yes?
So if I, say, swap to letters of that array, then I would get a transpose.
Let's find out. I don't know if it's settable. Let's say settable, so it's settable. So first, show npm. Now let's do m.strides equals 816.4. And show npm. And there you are. You've transposed it in some weird way. You've quote transposed a three-dimensional matrix. Okay? So I mean, this is cool actually. I mean, the fact you can just flip around the strides and it has this sort of impact is pretty neat. It doesn't quite fit in your head if you're thinking from a very kind of abstract mathematical point of view, but from a data analysis and manipulation point of view, it's beautiful. I mean, it's powerful, it's nice, it's wonderful. And again, you know, when you have some data structure where you can do all these sorts of things, there are a lot of ways in which you can use it to do useful calculations. ndim is the number of separate dimensions. This is a three-dimensional array, meaning there are three different indices. You can't change that. I don't know what that is. This is some sort of not get single element, single segment buffer for discontiguous. I think we messed up our array by changing the strides. So I'm going to change them back. 6284. Okay, so this is the raw underlying data. of this three-dimensional matrix. There it is. Okay? So again, there's all this stuff you can just get at. It's a buffer type. And I think this buffer type, which is supposed to be raw data in memory, is something that's going to be added into Python 3K. So it'll be a standard part of Python soon. Flat is something that allows you to iterate through the entries of the matrix efficiently. So for example, for a matrix, you can say list of flat, and it just gives you back the list of all the entries in the matrix. But even if your matrix were huge, just doing m.flat would give you this iterator that you could work with very efficiently. And you can also, you can just set things in, you can get the flat version of the matrix. So it's more than just an iterator, I guess, because you can set it, and set a particular item in there, and then that affects the original matrix. So if you have some algorithm, and for a moment, it'd be really nice if you could just think of your 7-dimensional array as one single long list of numbers, and you want to change every other one or something, just do the array.flat, and you get the flat version, and you can do it. So I mean, these ND arrays are kind of the ultimate tool for just manipulating a bunch of homogeneous data in memory, the ultimate n-dimensional spreadsheets. C-types, I haven't said much about C-types. C-types bears some relationship to Python in a sense. It allows you to access external compiled code from within Python. And in particular, if you have a C or C++ library function, or in Windows some sort of standard library function, you can call it directly from Python without ever touching Python or using a compiler at all. You just have to have enough information about the layout of the dynamic library that you want to call into. And it's something that's a standard part of Python. It used to be an optional package for Python until Python 2.5 about a year ago, but now it's a completely standard part of Python. I haven't used it much. My main use of it initially was to benchmark using it versus Pyrex to see which was faster, and Pyrex is faster. And so I didn't really have a personal use for C-types. And sometimes it can be a bit flaky in that if things aren't laid out just right, bad things can happen. The problem is all the linking happens at runtime, and this can, you can test your code all you want, but then when you deploy it somewhere else, there's this linking with dynamic libraries only at runtime, so it can be a bit flaky. That's been my experience with C-types. That said, it is a powerful way to call into external C libraries where you never have to touch Python at all. Actually, Robert, do you have any comments about C-types? I don't know. You should, but maybe, I don't know.
Well, we're hoping to make C-types and Python work better together.
Good. Okay, so better C-type Python integration would be good. I would actually be very, very happy if somebody gave a talk on C-types in the SAGE seminar. I'd like to learn a lot more about them. I mean, I have used them some, and Josh has. So here's some other underlying information about an ND array. There's lots and lots of these functions. And here's a nice table from the Numpy book, which just summarizes all these attributes of ND arrays, whether or not they're settable, and what they do. Okay? So moving on, and you can just look at that in the slides. So now, for the rest of the talk, I'm going to work with a two-dimensional 3x3 ND array instead of a three-dimensional one, so that it'll be just a little easier for you to think about. It's a little less abstract. So here we go. This one has float entries instead of int entries like the previous one had. But again, notice that the types of the entries are not Python floats. They are some sort of special NumPy object that wraps a double precision machine float. So they're really, really different. And, well, I mean, they're not really that different since Python floats are implemented using doubles as well. But they are a different data type, so you have to be aware of that. It could cause you problems. You can change entries. We already did. You have flags, everything like I just showed you. Let's move on. You can load and save NumPy arrays to disk. So here's an example where I take that NumPy array and I pickle it, and this gives me a string representation of the underlying array. The raw data the sequence of doubles, it spits out in some sort of binary format that doesn't print very nicely in the notebook. But that's efficient to read in and to write out. And then here you're loading it back. And by the way, this capability of dumping and loading matrices, especially Numpy matrices, is extraordinarily important in the context of massively parallel computation. Because there you have problems where you need to move data around. The data is stored as matrices, or you need to share bits of matrices on different machines. So it's really important that you can easily, efficiently turn a piece of a Numpy array into something that you can stream over the network and then use on another machine. And there's a lot of research that's going into making that faster by, for example, Brian Granger. He's actually, this guy Brian Granger is doing a lot of work on extending Numpy to work with distributed arrays. So you have a Numpy array, maybe a three-dimensional or n-dimensional Numpy array, and you're the sort of person whose typical computer is, say, an 8,000 node Xeon cluster with, say, 8 gigabytes of RAM on each machine. So that's kind of like an old machine in the Texas Supercomputing Center in Austin. And you have a very, 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 very large matrix, and you want to work with it. And you have an algorithm that you can express just fine and run for small matrices. So you want some way of distributing that matrix in memory over this massive cluster and doing operations with it and so on. And this is something that Brian Granger is working very hard on. Is a NASA grant for doing distributed array computations. So you might think that if your array has so many entries that you can't fit it in the memory of your 8 gigabyte computer that you're stuffed, but that's not at all the case. You could certainly, there are ways to put some of the matrix in one computer, some of the matrix in another, and so on, and then make the entire usability experience just really, really clean. And that is being worked on. Oh, by the way, it's really easy to convert back and forth between Sage and Numpy matrices. So here's an example of a good old-fashioned matrix over the integers, 3 by 3, exact integer entries. If you just call the Numpy method on that matrix, you will get back a Numpy array. Notice though, since those are arbitrary precision Sage integers, the resulting array just has D-type object. So you get a lot of the functionality I showed you on these generic Numpy arrays. These entries are Python objects, but they're going to be really slow. Like if you do matrix multiplication, it's going to be dog slow. And a lot of manipulation of slicing in could be okay, could be slow, who knows. And then things like computing the mean and the standard deviation, that sort of stuff could easily be very slow compared to what happens if you specify the data type. Here, I specified that I want to use int as the data type, and it uses 32-bit ints instead. So you could have issues of overflow, etc., but at least it's a lot faster. So these are two functions or one function really to remember, which is given any Sage matrix, you do matrix.numpy and then give optionally the data type, and the result will be a Numpy matrix back. But you can also go in the other way. If you have a Numpy matrix, you just say matrix of it. So for example, take this Numpy matrix with int entries. If you say matrix of it, you get back the corresponding Sage matrix, as you can see. Okay, so you can go back and forth easily between Numpy and Sage matrices. At present, there is no implementation of something that's kind of in between, where you have a Numpy matrix, but it's optimized for entries that aren't just some generic object type, like maybe entries that are interval arithmetic entries, so MPIR entries, or entries that are finite in a finite field, or GMP entries or whatever. There was a lot of talk about a coding sprint project to do this at Sage Days 8, but it never happened. And I think part of the problem is that there are no, except for generic object, there are no examples of implementations of Numpy arrays where the entries don't all have exactly the same structure, where they're not really homogeneous. So nobody's done that yet, but I hope it happens. It would be really neat to have kind of a really fast Numpy array that does arithmetic over a finite field. or it does arithmetic with multivariate polynomials, or something like that. I mean, we have them in Sage, but again, NumPy arrays, they're just like the entire design philosophy is so different than the philosophy for Sage matrices that you want to fully support both. And as a user, you want to know about both of them. Just because, I mean, it would be kind of like, it's kind of like if you're really into commercial software, it's good to know about both Mathematica and MATLAB, because there are some problems that are better in one and some that are in the other, despite their advertising to the contrary. Another difference, the data types of Sage matrices depend a lot on the base field of the matrix. So for example, here, if you make a matrix over the integers, its data type is matrix integer dense. If you make a matrix with complex double entries, its data type is matrix complex dense. There's a whole bunch of, actually, it's matrix complex double dense. There's probably a dozen, at least, different data types, and they fit in a class hierarchy in Sage. In NumPy, there's just one type, ND array. So you don't have this big hierarchy of different types. So type of A is numpy.nd array. Every single NumPy array is of data type numpy.nd array. And the thing that impacts where the coefficients are is just a property of the matrix. Okay? And they can get away with this because, I mean, for them, a NumPy array is just this homogeneous chunk of RAM and then some stride information. And that's it. So it's possible to have this flexibility. Let's see. Okay, now I'm just going to show you a couple of functions. There's a lot more than just, I mean, there's a ton of functions that are methods on NumPy arrays that give you information about them. And there's also tons of functions you can call that are not methods on NumPy arrays, but are there anyways. So you have to watch out for that, since that's something somewhat different than what you find in Sage. So here's an example of just one of the many, many methods on NumPy ND arrays that I mentioned at the beginning of the lecture, the clip method. So here, given a NumPy array, let me show you the original one and the clipped version. Show in PA. So the original randomly generated matrix looks like this. When I call clip on it, it just truncates all the entries that are above or below minus 0.5 and 0.5. So, you know, if you're drawing a 3D picture, for example, and you've computed all the points that you want to graph, clipping is often a good idea because you want to, you know, if a couple of the points are 1,000,000 and the rest of the points are small, the scale will be thrown off if you don't clip the data first. I'm sure there's lots and lots of other situations where it's a good idea. Computing the conjugate, rounding all of the entries, computing the trace, summing up all the elements in the matrix, summing just the rows in the matrix. There's the sum command even is much more sophisticated in a sense than Sage. You give a what's called an axis, which is basically like it's a slice type thing. I don't actually understand it. I looked at the documentation, tried some examples, and it doesn't work the way I think. So I don't quite understand it, but it seems extremely powerful. So you can have like a 7-dimensional array and do some sort of weird sum of sub-matrices along some axis. I guess it's sort of like imagining taking some higher dimensional array, choosing an axis, and then summing all the matrices you get along that axis. What? I don't know. Looks like it. Yep. So there's something, 0 and 1. Okay. I only looked at it for about 2 minutes, so it's not that I tried really hard to understand it and I can't. It's just that I was just going to look at it for 2 minutes. Here's an example. There's a bunch of statistical functions. So taking our same matrix, here I computed the variance of all the entries in the matrix, the standard deviation of all the entries, etc. The square root of the variance is the standard deviation, the product of all the entries. So that's, again, the sort of thing you're just not going to find with Sage matrices. Compute the product of all the entries. I mean, what the heck does that mean to a mathematician? To a pure mathematician, it's just ludicrous. But to an applied mathematician, it's probably a completely reasonable thing to do. I don't know. But you know, it's the sort of thing where, you know, having a special function just for doing that, that's in a sense vectorized. That is, if you've got your data and you want to compute the product, you really don't want to have to go through and write a for loop to do that. Because if you do, it's going to be slow. This product function is undoubtedly extremely fast, as fast as you can hope for. So, all right, so there's a couple of other things. Let me say one more thing before you go. You definitely want to try numpy.linalg.tab. There's a whole bunch of packages of stuff for linear algebra here. And there's also numpy.fft with a whole bunch of different fast Fourier transforms that you can apply to a matrix. So you want to look around at these sorts of things. If you make a NumPy matrix M and do m.tab and don't see the function you want, it doesn't mean it's not in NumPy. It just means they didn't bind it to that object. So these functions, you call them on a matrix rather than using .tab. Okay? So that's the one other thing to know. Other than that, there's a 350-page book on NumPy. There's a ton of other things, but I think I've given you enough of an introduction so that you'll know that in certain contexts, NumPy is the way to go. And by far, it's an amazing system. Okay, thanks.